So if you look at the grand challenges, not only for the most developed countries, but globally. So we are facing with challenges related to energy, water, environment, medication, disease, prevention, food security, etc. So most of these things, especially environment, sustainability, and energy, that are interconnected to each other. So in this specific case of environment, we're talking about very high CO2 levels, high salinity levels in the oceans, and increasing atmospheric carbon dioxide, etc. So in terms of the sustainability, we're talking about who has access to what, in terms of which parts of the world is accessing to the new technologies, especially as Professor Marucho said, like cleaning freshwater resources or brackish water resources. So in order for us to sustain and meet the global needs, so we are facing such grand challenges. When we talk about environment and energy, these two things cannot be separated from each other. So we need to power up the globe. We need to continuously supply energy for both industry and residential areas, etc. So while we do that, obviously we are currently still and probably will continue to rely on the existing infrastructure. So what does that mean? This means that we'll be continuously depleting, exploiting our fossil-based fuels. Infrastructure is already there for about a century now. Of course, although there are renewable attempts coming up, but it is not very up to the level of continuously provide us the power that we require, which is already in the exponentially increasing rate. So the alarming issues is not only the atmospheric carbon dioxide levels. So earlier back in 2012, back in 2016, people were talking about there's a tip-off point for atmospheric carbon dioxide. So if we go beyond 400 ppm, it's going to be no turning point. We already passed that. So we are currently in uncharted territory. So we don't know what's going to happen, how we're going to be able to retract this back. But hello?
Yeah, I think somebody has. Is it okay?
Can you see the slide again?
Yeah. Yes.
Okay. I'll continue. So I was just saying, it's not only the atmospheric carbon dioxide is the problem. It's also the salinity, the acidity of the oceans are going high. So this is a NASA image has been captured from the satellites in the last few years. So as the salinity increases, so we're going to affect the marine life. The shelled animals will be affected. So it's going to affect the food chain. So if the food chain is affected, so we all get affected. So to deal with the toxic emissions, it's not only the carbon dioxide that we are concerned about. There's also uncombusted methane. There is methane also, lying on the ocean beds as hydrate sediment. So in case of an uncontrolled release of this methane, which is believed to be known to be 30 times more effective in terms of trapping heat in the atmosphere. So these are really major concerns. And on the other hand, with the chemical industry activities, we also keep releasing other toxic emissions such as NOx and SOx. So we have to do something with those. Of course, although there are existing protocols, existing processes that are in place, so we always keep looking at some more effective processes to deal with these issues. So where does the problem really coming from? So the energy consumption activities during our daily conversation, we always blame the transportation, but it is actually the industry related and ecological or agriculture related activities is contributing the most the most effect on the toxic emissions. So then we would like to take a look at what is the root cause of all these emissions coming from. Obviously, as you all or most of you are aware of, we are still heavily dependent on the fossil fuel based infrastructure, as I just mentioned in the earlier my presentation. So there's a good thing about natural gas, which is on the rise in the last couple of decades. So which is considered to be cleaner source of fossil fuel. So we have still in this table, you can see that still heavily depending on natural gas, oil, crude oil, gas liquids, and coal. So if you break down our 24 hours of energy consumption, and really, less than 3 hours of our daily energy is powered by the renewables. This is on the rise. So a few years ago, when I had this slide, I was here showing in the scale of seconds, but now, thanks to the very dominant research on especially biomass and solar, so we keep on seeing the trends on the rise for the renewables. But we are still dependent on the fossil-based fuels. So where is the problem? So we keep using these fuels. We will probably continue to use these fuels for several decades. So if we leave the environment by itself, so it has its own internal balance to deal with the carbon. So the environment doesn't have carbon tax notion, so it doesn't have to deal with the very complicated political science matters. But if you leave it alone, so it's gonna eventually find its own equilibrium. So oceans, rivers, lakes, ponds, inner seas. So these are forests. So these are excellent absorbents or adsorbents of the CO2 or other toxic emissions. But if we emit more than that we are supposed to emit, then that's the problem. So where does this happen? Obviously, it happens from the industrial activity. So from very heavily energy-intensive processes are still relying on oil, coal, or mostly natural gas. So the current status is, yeah, we have this carbon. So what we do with this carbon is we capture it. So the trend is to capture it. Carbon capture and sequestration, CCS, the most common three letters acronym is used for the current state of the art. So for those who are not really familiar with the carbon capture technology, so it's mostly taking care of the three well-known processes. So the post-combustion is you let everything combusted, and after the combustion takes place, so you take all the effluent gas to the separation. So this is one method. The other method is pre-combustion and oxy-fuel. These are really pretty actually common to each other. So the pre-combustion and oxy-fuel, it uses either air or pure oxygen through the air separation unit to deal with to treat the combustion before target CO2. Then it is sent back to the power and heat generation. Yeah, it is working fine. Of course, with the emphasis on the different materials that are used in these processes. So the capture efficiency, the energy consumption that you will be using in the capture process will be, of course, changing. So after that, what happens? We take this captured carbon and we sequester it. Of course, for a good reason. So we just don't want to swipe it under the carpet, but we just use it for enhanced oil recovery purposes. So what does this mean? If we have an oil or gas well, so we would like to maintain the upstream pressure. So we need to balance the reservoir pressure. So that is a very tricky process. So we keep on injecting some nasty fluids that we capture into the depleted reservoirs or currently active reservoirs in order to be either to hide the problem or convert the problem into an opportunity. What I believe, it's not this is not the context of this talk today, but what I believe is instead of CCS, we should be leaning towards CCC, which is sequestration is replaced with conversion. Especially in the last 5, 6, 7 years, there has been enormous efforts on working on the conversion aspects of the CO2 into some raw materials, methanol or other useful chemicals. So, but no notable breakthrough that has been proposed that will revolutionize the entire world. So there's another aspect of what people do, including myself. People deal with how to enhance the efficiency of the capture processes, and also how to reduce the cost of the capture processes. People look at two different things. They look at either solvent chemistry, or they also look at the powder chemistry. So they look at porous materials. So engineering the porous materials is quite challenging. What is currently being done is, I said, people work on crystal structures or amorphous structures. So they work on different crystalline systems, or they work on different polymer systems in order to, through changing the pore size, distributions, pore volumes, surface areas, etc. So the affinities or the capture capacities or gas separation performances are being targeted. So what is very simply what is being done is, so they have people have been working on using different core materials. They're linking them with the different linkers. So they work on the linker chemistry. So and they target very specific gas capture performances. This is a fascinating area. I myself have been working on this area for more than a decade, and I will continue to work on this. But although we publish very good good articles, especially the last year journal in Nature Energy, we keep on showing very high performances, very nice smart materials that has memory effect, etc. Still, there is a gap that needs to be filled. What do I mean by that? So we as chemical engineers are very conservative. So as most of you, or perhaps all of you, will agree that while it is working, don't touch it. Especially in the lab, don't disturb it. So keep it running. Obviously, we keep on researching other things, but when it comes to the industry level, so technology readiness level, there is a big barrier. There's a big gap to jump from technology readiness level from 3, 4 to 6, 7, or 8. It's a dream. So which means is currently existing amine-based absorption technologies have been used since 1950s, 1960s. So the gap, the barrier, the hurdle that we have to jump over is quite high. So from switching from the porous materials to the solvent-based systems, so what's the notion of that? Because the porous materials are very heavily sensitive to water content. Very few of them can be very stable and can be reusable under the very harsh conditions that we are dealing with in gas absorption world. So also there is also one important thing that we would like to I would like to emphasize. So as a chemical engineer, we also look at the processability as well as economical feasibility, right? So if there is an existing infrastructure that is built and designed and operated for a liquid system, so it will be very costly to retroactively change all the existing infrastructure of the existing plants. So that's why finding and working on some sort of liquid systems that will be used with the very minor retroactive or retrofitting modifications of the currently existing infrastructure will be a champion. That's how I see. That's how we see in my research group or through my collaborators. And for this reason, we look at we have started to look at evaluating different liquid systems in the last several years. So if you're looking for a nice academic or an industrial or an environmental problem, these are all interconnected to each other. Carbon dioxide capture or beyond, or including other different toxic gases, it's a very big challenge. So that's the one of the main motivation points of my research. The other issue is, it's not, I keep on talking CO2, but if we talk about, if we consider the pre-treatment or pre-treatment of the natural gas before the LNG or before the GTL, gas to liquid, or before the liquefied natural gas unit. So all these processes will include several pre-treatment processes. So gas doesn't come by itself pure. So we have to deal with benzene, xylene, and toluene extraction. Or we have to deal with the fuel desulfurization. So there is SO2 in the system, especially in the Middle East. There is a huge H2S content in the existing natural gas reservoirs. So targeting these toxic gases is also a very interesting area, and industry has been looking for alternative and effective solutions. So energy storage, also another problem, as I mentioned in the earlier slide. This is considered as one of the big grand challenges. So deep eutectic solvents as a solvent can also has been considered as a very crucial component for batteries and for other sorts of energy storage medium, such as methane storage. This is also another focus area that we consider in our research. So as the complexity of all these materials go high, the amount of time that needs for the development and the amount of time that needs to the commercialization, it also goes high. So this paper was published in 2010. So ionic liquids were towards the very complicated side of the graph. Initially, deep eutectic solvents wasn't there. Perhaps it wasn't as popular as back then as it's now. So I added this manually here, trying to emphasize that. So deep eutectic solvent is in the picture now, and we also believe that although it is not as complicated as ionic liquids to deal with, but it still exists on towards the high end of the the line, the curve, because of the industrial barriers or other processability factors that we have been considering. So from this perspective, from this concept, so in my lab, I'll deal with all these different challenges: gas capture, gas storage, gas hydrates, some pharmaceutical applications, and process optimization. So the materials that we deal with in the last few years, definitely deep eutectic solvents is taking most of our time. Ionic liquids also has been the starting point of the deep eutectic solvent research, and the research emanation that we have, the capabilities that we have is, I am trained as an experimental chemical engineer, so experimental thermodynamist. So which means that measure what is measurable and make measurable what is not so. I added theoretical capabilities in the last decade to my research emanation. So mostly I deal with density functional theory in order to observe the short range interactions and try to understand what experiments doesn't tell us. So I'm going to show you a sample of my research activities and try to explain how we use deep eutectic solvents for gas solubility measurements. So here we go. Before you start, obviously you need to know what is the limitations, or what is the target that we're after. We have been considering deep eutectic solvents as a capture agents for two purposes. It can be used for pre-combustion, or it can be used for post-combustion. In the case of post-combustion, we're talking here about lower pressures, and we're talking about higher temperatures. So the pre-combustion is higher pressures, obviously, and so which means that this puts us in a position that we need to stretch the limit of the materials that we prepare or the materials that we consider, and we need to obtain higher pressure data up to 50 bar, and in some cases even beyond. So for those who are not familiar with the gas solubility experiments, there are several ways to do this. So you can set up your own equipment by using a simple pressurizer or autoclave. You can monitor the pressure drop when you charge your system, when you charge your gas into your system, and you can quantify, do the mole balance, and obtain how much gas is dissolved in the solvent. But there are some commercial tools also already available. These are based on few different backgrounds. So you can use volumetric based or thermal conductivity based, or you can use gravimetric based. So I have been using gravimetric based equipment, which means that so you directly measure how much gas is going to the solvent side, absorbent or adsorbent, doesn't matter. So you see the weight increase in live mode. So in situ mode, you can observe what's going on in the cell in terms of adsorption or absorption. So this part of technique also gives you another flexibility that in case of a swelling, you can see directly, because gravimetric method use the volume of the sample. So in case of swelling, your volume will be going high. So in terms of your volume will be going high. In case of your volume will be expanding. So you have a sudden drop in the buoyancy. So which means that you will have a direct measure observation of the swelling effect. One of the reasons that I put this slide on is the current problem with the amine-based systems is the little guy that you see here. The reboiler of the regeneration column is probably using huge amount of energy that has its own CO2 tax that is considered to be emitted to the atmosphere. So this process is very energy intensive. So chemisorption makes it very effective, but at the same time, chemisorption makes it very energy intensive, because at the end of the day, you need to strip the captured gas back onto the purified effluent stream, which can be considered to be used as enhanced oil recovery purposes. So what's the point? So we keep on cleaning the system, but at the same time we keep on using huge amount of energy here in the reboiler. What can be done? Yeah, people have been considering different activators, piperazine, triazine, to enhance the capture performance at least, so that the energy, the unit energy is used per removing the amount of CO2 regeneration will be reduced. But there's another perspective here. Some of my colleagues are working on the process intensification or process optimization. So they are considering the rest of the plant. They're considering rest of the hot or cold sources, so that they can integrate those process streams to this absorber, desorber, or CO2 capture columns, so that the energy amount that is required in the reboiler is reduced. So all these are nice efforts, and there are very valuable research still going on. But our perspective is to know, what if we come up with different materials, different solvents that will still work, though they will still work in the existing setup, but at the same time, it's going to be very less energy dependent when it comes to the regeneration. So this is the main motivation. So we start our journey by considering very common ionic liquids at high pressures. High pressure, is like 200 megapascal. This was quite high pressure that we tried in the beginning, just to be able to see the experimental capabilities, at the same time material capabilities. Obviously, we hit beyond 100 megapascal. We hit a certain position that the amount of CO2 has been going down. So we decided, okay, how come this is possible? We keep on increasing the pressure, and the material should be getting more. It should not be going down. At least it should be staying in the equilibrium. Then we realize, okay, there's a swelling happening here. This is what I mentioned a few minutes ago. Once the swelling happens, the volume expands. If the volume expands, the method that we're using is, as I mentioned, was the gravimetric method. So the buoyancy suddenly drops, so it registers that less and less amount of CO2 is being absorbed. So this was a concern. Of course, we went back and corrected this at the lower pressures, but we realized that some ionic liquids might have issues with the swelling, and also we don't really need to work with very high pressures because of compression. Compression is another concern or another layer of constraint that we might be considering while optimizing the overall process. Ionic liquids are fantastic, so we still work with those in different research fields. But I was just able to attend the last portion of Professor Mauriccio's talk. She also already mentioned that these are very high cost materials. So they are not produced in bulk. If so, very few targeted selected ones are being produced in bulk. So, and also very high viscosity, pumping requirements. So these are really concerns and limitations that we have been considering. So what are the other alternative solvents? Obviously, deep eutectic solvents. So deep eutectic solvents came into the picture, came into our attention radar several years ago. Of course, if you're working with ionic liquids, you cannot miss to work with deep eutectic solvents, right? So I'm sure before me, other speakers have been talking about the definition of the deep eutectic solvents. So basically, you have a hydrogen bond acceptor and a hydrogen bond donor. You bring them together, and they form a eutectic mixture, eutectic solvents. So so this is what we use, what we have been considering for the gas solubility measurement. So what are we after? We'd like to go and lower the CO2 capture cost. We would like to obtain higher gas solubility, which the solvents that we're dealing with, we would like to have environmental compatibility. Natural solvents are also in our scope. I will talk about this. The most importantly, the solvents that will be able to substitute the current state-of-the-art solvents with minimum infrastructure redesigning. Okay, so we have lots of alternatives in terms of dealing with the generating the deep eutectic solvents. So we started with with basic system, very famous choline chloride. We coupled it with levulinic acid several years ago. So the main motivation why to selecting these materials was we wanted to be biodegradable system and low or non-toxic system, so that we can have a nice background setup for the system, so that we can go forward to the actual CO2 capture performances. So we dealt with the physical properties. So this was sort of density measurements or viscosity measurements. I'm not going to talk about them. So we started with these things. But what was interesting for us was the main motivation was the CO2 solubility data. At several different isotherms, we obtained up to 30 bars, around 2.5 millimole per gram of CO2. And in the beginning, we were thinking, okay, we didn't hit the jackpot, but still there is a opportunity here. So we started to look at the kinetics. the kinetics was not so quick, but not so slow. Okay, so especially at the lower pressure side, we were talking here about reaching to equilibrium within 8 minutes. And as we increase the pressure, we have seen around 10, 11 minutes, we have reached to the equilibrium of the CO2 solubility. So we wanted to compare our results with the common state of the art. There is no direct comparison. We could have measured it. We could have measured the monoethanolamine or MEA in our system, but we didn't because of time restrictions. We just pick one of the published data. So they are not directly comparable, but we are still in the ballpark. Okay, so which means that the choline chloride levulinic acid that we selected, 1:2 ratio, was pretty much giving us a similar result in terms of CO2 solubility. So for those who are not familiar with the CO2 capture, some students might be off this area. So for gases, if you increase the temperature, the solubility will go down. So if you increase the pressure, the solubility will go high. So that's how we compare these two different data sets to each other. So, but what was striking us the most towards the end of this paper, we wanted to see the corrosion effect, because MEA or amine-based systems they are not considered to be used without having a corrosion inhibitor in the system. So you must have a corrosion inhibitor because these are corrosive materials. That's one of the main issues with the amine system. So it has its own side effects to the processing equipment as well. So we had a very simple corrosion cell from one of my colleagues. So I accessed that equipment. I said, hey, let's give it a try. So we followed ASTE standards to do the corrosion test. And at the end of the corrosion test, so we have repeated this 3 times, the choline chloride levulinic acid was giving us 0.027 millimeter corrosion per year, whereas MEA is almost half a millimeter per year. So this was fantastic. We were expecting to see that, but 20 times less corrosion is really phenomenal. So this was one of the selling points of this work. They are also, we consider this system as decent absorbent performance and also phenomenal corrosion rate has been shown here. We kept on trying different deep eutectic solvents. We call them so-called NADES. Instead of DES, we call them NADES. So this is oftentimes when you read papers, you see this terminology. This means natural. So natural deep eutectic solvents means so the hydrogen bond donor and the hydrogen bond acceptor, they come from the natural sources. In some cases, you look at let's say amino acids for the hydrogen bond acceptors, or in some cases you look at citric acid, malic acid, etc. for the hydrogen bond donor. So we decided to we were influenced obviously with different authors, with different work, but we wanted to see the application of the NADES to gas solubility. So we decided to group them into 2 different areas. So choline chloride based NADES and amino acid based NADES. So this work was done, and we targeted carbon dioxide, and this time we added nitrogen to the carbon dioxide because we wanted to see the selectivity or gas separation performances of these materials. Yeah, we gathered the data, but this time we got better performances. At around 50 bar, we increased the pressure from 30 to 50 bar to stretch the limit of the equipment. So obviously, we are here talking about 4.5s, 4.8s, CO2 millimole per gram of deep eutectic solvent. But interestingly, I wasn't expect to see that in several cases, nitrogen is giving higher solubility. So that was interesting. And for the amine systems, it was the same. So nitrogen solubility was higher than the CO2 solubility. So this has an effect on the obviously on the selectivities. Um, One thing that we specifically observed here was the absorption and desorption curves. So many people doesn't really report on the absorption desorption because I believe that this is quite essential and very crucial important information for us to be able to see how does a solvent behave in the case of releasing of the pressure. Because most of the times you see hysteresis. So when the hysteresis happens, so it means that you might have a very complex interdynamics in the column. So it might lead to a sudden expansion, local expansion, volume expansions in the column in an uncontrolled way. So that might lead to some sort of flooding, perhaps, or some local pressure building might be a very unpleasant case that we would like to avoid in the regular, smooth, steady state operation. So DES and NADES did not really show us this sort of behavior. It was very smooth absorption, desorption, no hysteresis, no chemisorption. No chemisorption that we observed. So which means that whatever we started at 0 point, we increase the pressure. Then when we come back to the vacuum point, which means we release the pressure, we were able to regenerate the system completely. I think I forgot to mention here, I forgot to include a picture here, a slide here that shows the repeatability.
You are muted, Mert. You are muted. We cannot hear you.
Your microphone is mute.
How about now?
Yeah, now it's fine. Yeah.
Yeah, it's good.
Okay. I hope you didn't miss much.
No. I think.
Okay. Let me pull up the slide again. Just a second. Can you see my screen?
Yes, we can.
Yes, we can.
Okay. Okay. So one of the issues that we also looked at was we claim that we work with deep eutectic solvent, but when we charge the gas into the system, we don't know whether this charged gas disrupt the eutecticity, disrupt the eutectic solvent, or which means that are we observing hydrogen bond donor goes one part and hydrogen bond acceptor goes one part. To be able to observe this, we run with my colleague some molecular dynamic simulations, and we observed that hydrogen bonding of in the case of here choline chloride and levulinic acid or other malic acid, citric acid, fructose. So we were able to see that both in the case of ionate liquid as a hydrogen bond acceptor, cation, anion, they are still interacting, or cation hydrogen bond donor, anion hydrogen bond donor are still in very much interaction with the with each other, even in the case of CO2 is introduced to the system. So this was quite nice to observe, and it was kind of a relieving point for us proving point for us that we are really working with DES here in the case of high pressure CO2 is introduced to the system. We also work with CO2, nitrogen. We also work with methane. For the methane system, we went up to 50 bars, 25 Celsius, and we decided to work with totally NADA system as a beginning. Alanine and betaine, choline chloride we used. We did not observe what we wanted to see in terms of energy storage applications. Of course, we are very away from the Department of Energy's volumetric storage thresholds, limits, but this is the starting word. So we were able to observe up to 3.5 millimoles methane per the gram of sample. We also have a selectivity issue here. So this is the challenge that we would like to overcome if you would like to separate uncombusted methane in an effluent system in which CO2 is heavily presented. So we would like to go beyond than 3:1 or 4:1 ratio. We need to talk about 15:1, 20:1. So this is something that it's on our agenda that they'll be working on. We have been also working on the molecular viewpoint of the storage, methane storage. So density functional theory really gives us very good insight of the material. So basically, we create our models. We use either Siesta, Gaussian, or Orca DFT codes. Then we move the calculated simulation results to the atom in a molecule platform to see exactly which part of the gas molecule is interacting heavily with which part of the hydrogen bond acceptor or hydrogen bond donor, because experiments doesn't tell anything about these things. Experiments tells us, okay, you get this amount of solubility and that's it. Then you can start, by using your experience, you can start speculating on or drawing conclusions on what might have happened, but DFT really tells us what's happening in there. So for the, let's say, for the case of methane, we have observed that hydrogen bond acceptor really does the heavy lifting, whereas hydrogen bond donors are taking the minor role while storing methane in the DES. Continuing on, we also last year we also we have started to deal with SO2. This is actually a part of a beginning of a project that we will be dealing with H2S as well. So this was a 100% simulation work, heavily dependent on computational capabilities, because experimental aspects of SO2 and NOx or H2S is very very cumbersome and very risky. So I will skip the theory. So we use Orca here again. We use the maximum available theory level B3 lip. We calculate the interaction energies, etc. Here we go. So what we have observed was how SO2 is again in contact with which active site of the hydrogen bond acceptor or hydrogen bond donor. Not only that, we quantified the interaction quality or the interaction strength, but also we were able to, on the right hand side, we were able to draw some isosurfaces to observe the type of the interaction, whether it is hydrogen bonding or it is Coulombic interactions or it is van der Waals affinities, van der Waals interactions, etc. So this was a very nice tool to set up initially to understand how SO2 molecules particularly interact with the deep eutectic solvent. So what we have found is SO2 is in interaction with both of the component constituents, HBA and HBD, but most of the cases, hydrogen bond acceptor is really dominating the interaction by considering the oxygen atom of the SO2 and the hydrogen side of the hydrogen bond acceptor. So this was quite interesting finding. So towards the end of my presentation, I would like to touch base upon some pharmaceuticals. We do a lot of work on the pharmaceutical in the last 2 or 3 years to consider deep eutectic solvents as an active delivery vehicles of the active pharmaceutical ingredients. By doing so, we would like to overcome the limitation of the water solubility of the most common active pharmaceutical ingredient that is identified by the World Health Organization. This is including antibiotics, antidepressants, analgesics, and some hypertension medicine as well. So we thought if we can come up with totally biocompatible deep eutectic solvents, not as in this case, and if we can enhance the solubility of these APIs, so we might have a different angle. Several things that we used was obviously solid pharmaceutical ingredients, but from the context of this talk, what I would like to mention is we also considered some gaseous pharmaceutical ingredients such as nitric oxide. So the nitric oxide case was chosen because of the recent pandemic, COVID-19. It is believed that nitric oxide can provide some desire. It has some desired effects of the COVID patients. It's been tried here in the United States in some different districts in some different states that the patients who are given nitric oxide, their recovery time has been slashed dramatically. Of course, this has to be proven through the clinical tests, but there is an opportunity there. So what we did was we considered the nitric oxide in the dissolved in the natural deep eutectic solvents, and the results were phenomenal. We submitted the paper to Molecular Liquid. It is still under review. It's in the first review cycle. So we have on the screen right now, you're seeing that we have been working on different pharmaceutical ingredients, which is already published data. I can show you that. So we obtain the solubilities through the molecular dynamics. We obtain I work on the density functional theories, and I see that how the deep eutectic solvents are closely interacting with the active pharmaceutical ingredients in this context. As I mentioned here, the enhancing the bioavailability of nitric oxide was one of the recent work that we have been dealing with. So the final remarks, I think I have a few more minutes. I'm not gonna, this is not detailed. So our perspective in dealing with the deep eutectic solvent is to, within the scope of this presentation, is to come up with effective performance at moderate and high pressures for gas solubilities. We have observed that low pressures might need work, especially at fluid gas conditions. We have been considering adding some synergetic materials to our deep eutectic solvents. Water content might be one issue, but in case of water content, yes, you will be increasing the gas solubility performance even at low pressures, but then you're going to introduce another problem, such as the desorption of the absorbed gas. So that might lead to, again, energy intensification issue. Swelling has not been a problem, or hysteresis has not been a problem. This is good. This is good for equipment design and processability of these materials in the existing infrastructures. High enough kinetics for quick absorption. It is not the highest in comparison to the current state of the art, but this allows us steady state pressure removal based pressure swing operations. And we have observed from the molecular simulations that the effect of HBA and HBD can be tuned for the target gas solubility. And I'd like to close my presentation with this couple of slides. I just moved to Kalamazoo in the Michigan. It's in the western part of the Michigan, close to Lake Michigan. It's a beautiful area, beautiful campus. So once the pandemic is over, I welcome all of you to come and visit us. So I'll be happy to, host the professors that have been participating in this work. So we can do maybe some sort of similar work, similar webinar or live event in our campus. We are considered to be one of the research institutes based on Carnegie Institute classification. Engineering campus has a dedicated space, dedicated area, dedicated campus. I haven't seen the winter yet, but they say it is pretty cold. So we'll experience this winter. So with that, I would like to acknowledge my collaborators, my funding agencies, and I would like to thank you for your attention. Thank you very much.
Okay. Okay, the session is open for some questions. Thank you, Mert, for giving such a wonderful lecture. So, anybody? Anybody you can ask, you can raise your hand. Yeah, so we have one question here. Professor Anki Reddy, my colleague, wants to ask.
Hi, this active pharmaceutical ingredient solubility you were talking about, right? And then you were using the classical molecular dynamics. So, but how you are going to really say some X are soluble in Y using a classical molecular dynamics? Is it like are there ways to?
Yes, it is a bit tricky. What we do is we look at once we do the molecular dynamic simulations. We have different angles to tackle the results. The one way to handle the the heavy output is to obtain the radial distribution functions, not from molecule to molecule, but cluster to cluster. So, for example, we look at the hydrogen bond donor to hydrogen bond donor, hydrogen bond acceptor to hydrogen bond donor, or API with either HBA or HBD. So once we look at those, we also look at the hydrogen bonding at the surface of the deep eutectic solvent. So the hydrogen bond distribution also tells us whether we have strong interaction with the system, with the API system, introduced API system, if it is strong enough or not. So we try to draw conclusions. So to be able to obtain the direct results, obviously we need experiments. Okay, so we are right now developing myself here experimental designs, so that in the next few papers you'll be seeing real experimental data that is coupled with the simulation work.
Yeah. Any more questions from participants? Yeah, I have one question, Mert.
Yes, Tamal.
Yeah, how does this reaction enthalpies compare between ionic liquids, the DES, and amines? Because it suppose it will depend. I mean, it will decide the conversion, how much it can, the uptake of the CO2. Did you measure the enthalpies?
No, it's a very good question, and it's a very valid question. To be honest, we haven't looked into that yet, so we are aware of it. And also, I am considering the effect of moisture in case of the flue gas. Because flue gas doesn't come with pure CO2, nitrogen, etc. So you will definitely have water in the stream, right? And once you have the water in the stream, these reaction enthalpies will be affected dramatically. And not only it will affect the reaction enthalpy, but it will also affect the desorption sequence. It's in my agenda, okay, but I have been focused only on the sorption performances for the time being. But in order to jump from the technology readiness level from 2 to 4 or 5, we must include the reaction enthalpies in case of different vapor phases are concerned.
Okay, then let us then thank Professor Mert for giving us a wonderful lecture regarding gas absorption. I hope all of you have learned, and those who are new to this CO2 absorption, CCS, what we are calling, I hope you can carry on and do something in your own respective area. So thank you, Mert. Thanks again for joining us.
Thank you, Tamal, for inviting for this wonderful event. Thank you.
Thank you. Yeah. So the next lecture we have with us